Welcome students. So here again we are with statistical mechanics and basically we are seeing classical statistics. The course code is BSCP3003. Myself, Dr. MD Shehzad Khan. Before starting this lecture on classical statistics, which is based on Maxwell's Boltzmann distributions, the prerequisite that is required is basic of classical particles. It means what is classical particles or which particles could be denoted as classical particles. Secondly, knowledge of permutation and combination. Very basic, very fundamental knowledge is required that one have studied in class 12. So the objective of present talk is Maxwell's Boltzmann distribution law. So this distribution law is applicable for classical particles only, and the distribution is applied, and in very beginning it is applied for the classical particles. A rigorous permutation and basic physics is required while driving this equation that we are going to see in our coming slides. Maxwell's Boltzmann distribution is applicable for macroscopic system, or we can say classical system, the large number of identical but distinguishable particles like ideal gas molecules or gas molecules in a container. This distribution tells us the way of distribution of total energy of the system among the various identical particles. And the constraint here will be the total energy, that is capital E, and the other one will be total number of particles, that is N. Within this constraint, the different possible distribution will be find out. The other important point is that the system must be isolated, which means that both the total number of particles of the system and their total energy should remain constant. That is the constraint that we are having, because it's a very hypothetical system. The third point is that the instantaneous state of a molecule is represented by a phase point in phase space that we have discussed in our previous lecture. Here we consider a 6-dimensional phase space, that is 3 position coordinate and 3 momentum coordinate. And in this phase space, all these position and momentum coordinates kept on equal footing. So in particularly, the phase space will be divided into large number of cells, let us say up to ith cell. And N1, N2, N3 till Ni, the number of molecules whose points lie in cell 1, 2, 3, I respectively in equilibrium state. The molecule in each phase cell have nearly the same energy. Let the energy E1 of molecule in cell 1 and E2 will be the energy in cell 2, and so on. Apart, one more factor that is included is degeneracy parameter, which is generally been denoted in my slide is by small g. The number of energy state, which is the number of energy state in the first, second, third, and ISF, and been denoted as G1, G2, G3, and GIN. So the constraint is shown here. The total number, that is N1 plus N2 plus N3 till Ni, it means summation Ni is constant. Hence, increment in individual ith component of N, that is N1, N2, N3, or let us say del Ni, all this individual summation will give 0 because of the constant that we have n is equal to constant. That is the fixed amount. Similarly, we see here that our E energy is also fixed. It means the number of particles that is being dispersed in different E1, E2, E3, or let us say EI states is fixed here. So the energy is constant. That's why its derivative, the small changes in energy, and that could only be contributed due to of changes in particles, is equal to 0. There is no change in energy. So basically, the distribution among the energy states like E1, E2, EI, and apart distribution among within the energy state, since they are degeneracy. So while doing all the distribution, we have to keep in our view that distributing among the different energy states, different compartments of energy state, and also the distribution will carry on in between the degenerate state as well. So the whole combination of distribution will be given by two terms that we are going to discuss. The first is how to distribute the number of particles among different energy states. So it could be done in the way that is given here. This one, okay, factorial n divided by factorial n1 n minus n1 factorial. It means just choosing n1 things out of n2. This is a simple combination rules that we have studied in class. Similarly, out of n, if we have chosen n1, similarly now we are having n minus n1 molecules, and from this our selection is for n2 molecules, and this process will continue till, and finally multiplying all this individual distribution among the different energy states, we get the term that is factorial n into, this is the product signature here, it's a product sign, I run from 1 to I, factorial ni, that is, it's a multiplication factor, okay. And here the second factor is the distribution among the degenerated state within a particular energy state, and it's same as that if we have, suppose, n particles or n balls, in different balls, and it is to be distributed among k containers, so that each container can get all the number of balls. It means it can get 1 ball, 2 balls, or all the number of balls. So in this case, the degeneracy the distribution could be given by this formula, that is W is equal to G1 N1 G2 N2 U1 to the power N1 G2 to the power N2 G3 to the power N2, and so on. And in concentrated form, small form, a multiplication factor is used, and this is the, when we multiply these two factors, that is that we previously discussed right now, and this one, we get the total way of distribution of number of particles among different energy state, and of course this energy state have some degeneracy as well. So the concentrated distribution, which means that we get from product of W1 and W2 is shown here, and then this final outcome will be applicable for driving Maxwell Boltzmann distribution, that we are going to apply Lagrangian method of multiplier, and we'll see that what is the outcome. So okay, these are some mathematical formulation given here, and W is the number of microstates that we have tried in previous slide, and taking its log, that is log, and using Stirling's approximation. And this approximation is generally used when x is very large. In this case, it is value, and on applying this Stirling's application, it comes to the last line that ln w is in ln summation I in I ln I and summation I ni ln gi. See, ni is the number of particles in different energy state and gi is the degeneracy associated with the energy state. For most probable distribution, know that W must be maximum provided N and E are constant, and on differentiating it to 0, differentiating and equating it to 0 for maximum value of W, the mathematical formulation is shown here. And multiplying equation 1 and with alpha and equation 2 with beta and adding them to equation 3, and thereby we get this particular differentiation. And one thing to remember here is that this Lagrangian method for determining Lagrangian multiplier method, here it is provided that if there is a function, the function we are having here is W and with some constant, and the constant is number of particles and number of energy state, total energy. This Lagrangian method is applicable when we have a function. Apart from the function, there are some constant given to that. In this case, this method plays a vital role in finding many of the properties of the equations. Following this, lastly we conclude with Maxwell Boltzmann distribution law, and it is given here. The formula is Ni by Gi, Ni number of particles, Gi is degeneracy, is exponential minus alpha and exponential minus beta I. Exponential minus alpha could be considered as some constant, and the basic term is exponential minus beta ei, where beta is equal to 1 by kT. It's a Boltzmann constant. So Kb is Boltzmann constant and the temperature is absolute temperature. And finally, the Maxwell Boltzmann distribution that comes to us is 1 by exponential alpha ei, that's the energy of IN state, and divided by Kb. So what it says, the Maxwell Boltzmann distribution, it says that if your energy is very small at a particular temperature, if your energy is very small, then the denominator exponential ei by kT become very small. Subsequently, 1 by some small is very large. It means it small energy, at very ground energy, the probability of finding the particles in ground state is high. That's why if we go on excited state, this probability of getting the particles to be at this state or their occupancy and those energy states get lower as you go higher in the energy state. And it is the basic Maxwell Boltzmann distribution. So, okay, and this was the lecture here, and it was being the lecture was being taken from with the help of this books, that is Statistical Developments from Suresh Chandra. It's a serious publication, and some of the parts were taken from SlideShare. Thank you.